Good morning, students. We'll continue with our today's lecture. So, in the last lecture, we had completed till vector manipulation, and the next topic which we'll start today is multiplying a vector by scalar. So, we'll take first scalar and then we'll go move on to the vector manipulations, different vector manipulation levels. So, priorly we'll be going with 1 matrix only, and then we'll move by 3 by 3 matrix and then all over calculations. So given a vector n, 2n means the vector's components are doubled. For example, if my n value is 3, 4 and 5, then if I multiply 2 by n, it will be 6, 8 and 10. So sorry, if I multiply 2 by n, that is n number, what will be my matrices? 3 2s are 6, 4 2s are 8. That is, it will double the matrices. That is multiplication. So which seems logical. Similarly, if we divide n by 2, its components are halved. Note the vector direction remains unchanged, only its magnitude changes. So displacement will not be there. That is, I cannot disarrange 4 first, then 3 and then 5. The arrangement remains the same. If I divide it by 2, it will become half its value, that is 3 will become somewhere 1.5 or 1.2. 4 will become 2. If I divide 5, it will be 2.5 somewhere. So it will be half of my values. So likewise, it's meaningless to consider addition of scalar to a vector such as n plus 2, for it's not obvious which component of n is to be increased by 2. So if I add n plus 2, it will be increased by 2, that is some value will be increased into 2 number. That is, if I add n plus 2 in the same matrix, 3 will be 5, 4 will be 6, 5 will be 7. Likewise, if all the components of n have to be increased by 2, then we simply add another vector whose components are equal to 2. So we'll add those components of that matrix with 2. That is just a easy and obvious way. How we can do vector addition or subtraction? We'll see that. Given vectors r and s, r is plus as well as minus, s is defined as r is xr, yr and zr, s is xs, ys and zs. So r plus minus s is equal to xr plus minus xs, yr plus minus ys, zr plus minus zs. So this is the combination value in the first equation 6 comma 7 which is given. Next is when I do this commutative, that is when I do it in a plus b format. How do I do it? That is, a plus b is equal to b plus a. That is vice versa. That is, if I add b plus a also or a plus b also, the answer should come the same. So the first example is 1 2 3 plus 4 5 6. Here if I add it like 4 5 6 plus 1 2 3, my answer will be 5 7 9, because even if I add 1 plus 4 or 4 plus 1, it is going to give me the same answer in the commutative law. If I am taking it in the non-commutative format, that is, I am doing the scalar subtraction. So subtraction will be different. That is, if I have the values, that is 4 5 6 minus 1 2 3 is not equal to 1 2 3 minus 4 5 6. So a plus b is equal to b plus a, but a minus b is not equal to b minus a, as it is proved in the summations. Because if I am doing a minus b, I will get the answer 3 3 and 3. But if I am doing b minus a, I will get the answer minus 3, minus 3, minus 3. So these are two different values because the signs here are different. So that is one criteria for addition and subtraction of vectors. So addition becomes commutative, subtraction becomes not commutative. So this can be shown on the graph. That is, if it is positive, it will be in the same upward direction, and all the two scales will be there, R and S, on the right handled format. That is, X is on the right hand side. Next is subtraction. If it is there, it will be in the opposite direction, and R minus S will be there, minus S will be there, normal S will be there, and R will also be there. That is, the not commutative values also will be there, and their own directions, that is R and S, actually on the graph also will be there. So position of vectors given at point P, x comma y comma z. A position vector P can be created by assuming that P is the vector's head and the origin is its tail. So from where it started, if we want to take the point P, we can take that point. But to take that somewhere, it should be on the head side of my origin. That is, from where it has started, from that side, wherever it is stopped on the upward direction or in the downward direction, but it should be at the starting point of my that particular range or line which I have drawn. Because the tail coordinates are 0 comma 0 comma 0, from wherever it is starting, the coordinates will be 0 comma 0 comma 0, so that is no use of taking point P on the starting origin. Consequently, the vector's magnitude, that is magnitude P, is equals to P of 4 square plus 5 square plus 6 square. That is the formula which we had seen for 3D Pythagoras, that is delta x square delta y square plus delta z square. So that is around 20.88, which is the last values which have been shown, and so that they have calculated 4 comma 5 comma 6, so which creates a position relative to the origin, which is somewhere like this, 1 comma 0 comma 0. That is unit vectors. By definition, a unit vector has a magnitude of 1. So the highest value of my unit vector will be 1. A simple example is I, where I is equal to, that is magnitude of I is equal to 1. Converting a vector into a unit form is called normalizing. So please keep this in mind. That is, when I am converting a vector into a unit form, it will be called as normalizing, and is achieved by dividing a vector's components by its magnitude. So as they have shown here, that they have converted a particular data into its magnitude, and that magnitude comes 1. How they have converted the data? X square, that is delta x square plus delta y square and delta z square, which came as an answer. 0 square is 0 and 1 square is 1. So magnitude of I is equal to 1. They have calculated it likewise. So which gives me in return the answer 1. So it's in the normalizing form. To formalize this process, consider a vector R whose components are x, y and z. The magnitude of R is delta x square, delta y square and z square. The unit form of R are given by this type. Like when I am doing it in the formalized format, when I am arranging it into a magnitude value, R of unit form is equal to 1 upon, that is 6.10, 1 upon magnitude R is x comma x y z. This process can be confirmed by showing that the magnitude of unit R is 1. To show that how it came 1, they have shown all the values, multiplied it 1 upon magnitude of R. So whatever the values were, they have been cut off with the help of x square plus y square plus z square, and which came into is equal to 1. To put this context into a considered conversion of R into a unit format, if we want to place this in a unit format, how do we, if we want to put a value, how we can put the values? 1, 2, 3 if it is there. 1 square is 1, 2 square is 4, 3 square is 9. 9 plus 4 is 14. So, and plus 1 is, 9 plus 4 is 13, 13 plus 1 is 14, root 14. If I do it in the unit form, 1 upon magnitude r is equal to 1 upon root 14 123, which gives me an value called as 0.267, 0.535, 0.802. So this is my actual unit form when I am multiplying each value by 1, 2 and 3. So this is giving me somewhere a product of my unit form. So what is the formula for unit form? That is the normalizing way. R unit R, that is R of U, is equal to 1 upon magnitude of R into the whole matrix which is being given, that is x, y, z. Next is Cartesian vectors. How do we form Cartesian vectors? Now that we have considered the scalar multiplication of vectors, vector addition and unit vectors, we combine all three to permit the algebraic manipulation of vectors. So now this is the combination of Cartesian vectors will be a combination of your addition, multiplication as well as unit vectors. To begin with, we will define three Cartesian unit vectors I, j and k. Priorly it was x, y, z or a, b, c. Now it is I, j and k will be the three Cartesian unit vectors that are aligned with the x, y and z axis. So they will be compared with the x, y and z dimensions of my graph or matrix respectively. So I is equal to 1, 0, 0, j is equal to 0, 1, 0, k is equal to 0, 0, 1. So these are the formalized formats of my ijk. Cartesian vector is given by r. So how is my Cartesian vector given by? A of I plus b of j plus c of k. So these are the comparisons and formula which has been applied to my Cartesian vector. This is equivalent to r is equal to abc, which can also be written, this can be written as ABC, where it stands for A is compared to I, B is compared to J and C is compared to K, which means that the magnitude of R is readily computed as magnitude of R is equal to root of A square plus B square plus C square. So any pair of Cartesian vectors such as R and S are combined as follows. If we combine both the sides R and S, that is head and tail, together, we can write it as A of I plus B of J plus C of K. S is equal to D of I plus E of J F of K. R plus S is equal to A plus minus D, that is these two are combined, R and S, of I because they have the component common I, plus B plus minus E of J plus C plus minus F of K, that is 6.17. So for example, if we calculate this with numericals, the answer which is going to come is R, the magnitude of R plus S is equal to S square, 7 square plus 9 square plus 11 square, which is 7 square is 49, 9 square is 81 and 11 square is 121, which is totally 251, and root of 251, the answer is 15.84. So this is the whole vector calculation, Cartesian vector calculation for unit format, which is a combination of addition and subtraction of two different components, that is magnitude. They priorly we were calculating magnitude for only one, that is either I or R. Now we have combined two magnitudes, that is magnitude of R as well as magnitude of S, and we have done the calculations. Next is vector multiplication. So how do vector multiplication provide some powerful ways of computing angles and surface orientations? Vector multiplication is done for the surface, that is the actual surface on which your area has been calculated, as well as the angles which it is forming with its various shapes. Mathematicians have discovered that there are two ways to multiply vectors together. So there are total two ways in which you can multiply a vector. First is one gives rise to scalar result, one which will give you an scalar output, and second one is the other is a vector result. So one can be one vector result as well. So we'll start with a scalar product. How do we multiply with a scalar product? We could multiply two vectors r and s. So there are two different vectors r and s by using product of their magnitudes. So we will multiply the product of their magnitudes through which we can find the answer. So magnitude of r multiplied, dot represents multiplication, magnitude of s, although this is valid operation, it does not give us anywhere, does not get us anywhere because it ignores the orientation of vectors. So it does not give you a formulated proper format because we don't have values. The dot symbol is used to represent scalar multiplication. We define two Cartesian vectors r and s and proceed to multiply them together using the dot product definition. So we will multiply with the dot product. So r is equal to what? A of I plus b of j plus c of k, and s is equal to d of I plus e of j plus f of k. Therefore, if I multiply r multiplied by s is equal to a of I plus b of j plus c of k into d of I plus e of j plus f of k. So if I make it a of I as common and I write the first one and I multiply b of j with whole bracket and again add c of k and multiply the whole second bracket, what I am doing, I am multiplying first component of my first bracket with the second whole bracket. So what I am doing, adding and multiplying each and every component with the second bracket, and by which I am getting an answer called as ADI into I plus AE I into j plus AF I into k plus BD j of j into I plus BE j into j plus BF j into k plus CD k into I plus CE k into j plus CF k into k. So this is the actual solution which we are getting by solving the second multiplication, that is magnitude of r into magnitude of s. Before we proceed any further, we can see that we have created various dot products such as I into I, j into j and k into k, etc. These terms can be divided into two groups, those that involve the same unit vector and those into reference different unit vector. So here what they have said is, we have in the multiplication we have found out that there are three possibilities where you have multiplied I into I, j into j and k into k. So there can be possibilities that I can be same here while multiplying, that is 2 into 2, or it can be 2 into 4, 2 into 6 as well. So different variations can also be there or similar variations also can be there. And using the definition of dot product, terms such as I into I, j into j and k into k is equal to 1 because angle between I, j and k is 0 degree. So as we are calculating surfaces and what you say or angles, the angles which are formed on the same directions will be 0 degree as they have said, and cos 0 degree is equal to 1. So we are calculating on the upper side, so that is the reason it's called cos. If it would have been the lower side, it would be tan. So this is a trigonometric way of originating at all the sides of the graph. So, but because the other vector combinations are separated by 90 degree and cos 90 degree is 0, all remaining terms collapse to 0. So, other all values will be cos 90 degree because they are on the upward direction but in the 90 degree side. So, as we are calculating the head side, not the tail side, so it will be collapsing to 0 and other will be 1, bearing in mind that the magnitude of unit vector is 1. So every time when you calculate unit vector, even if you solve everything, the unit vector answer will be 1, and we can write magnitude of s into magnitude of r cos beta is equal to AD plus BE plus CF. This is the final answer what we are getting because I into I is 1 and other all are 0. I into j will be 0, I into k will be 0, j into I will be 0, j into j will be 1. So by putting these values, the last answer which we are getting in 6.22 is AD plus BE plus CF. This is the last product. So with that dot product, if we try to solve these example, this is the answer, or this is the solution which we are getting, which I'll again explain it to you in the next lecture. We'll stop here for this lecture. Thank you.